Hello, welcome to the BEC1 Applied Healthcare Statistics webinar overview. My name is Christine G, and I am going to be hosting this, and it's just an overview of some of the important material in Chapter 4 that is on hypothesis testing with inferential statistics. And here, as always, I have graduation pictures because it's just a wonderful time, and really want to see more students at graduation ceremonies, and highly recommend you attend one if you're able to. And love meeting students that come out to it, and the speakers are amazing. So you can do this, just hang in there, and let's go ahead and get started with the material. So we're going to be going over the general logic of hypothesis testing. And sort of what hypothesis testing is about, you're looking at a sample of the population. So it could be a sample of trees, it could be a sample of people, it could be a sample of drugs, and you're looking at that sample so that you can make conclusions about the population. So you want the sample to be large and match up with what the population looks like, but it's going to be smaller. And it just is not practical to go out and survey everyone in the population. And so it makes more sense to use hypothesis testing and then make conclusions about the population based on a good logical sample. So first thing that we're going to be looking at are the steps involved in hypothesis testing. And there are 6 of them, and you can find them in your ebook on they start on page 83, I believe. So the first thing that you do in hypothesis testing is that you state the hypothesis, both the null and alternative versions. So we're going to go ahead and look at this and figure out what the null is and the alternatives. So here we have a scenario. A course mentor for chemistry believes that studying the chemistry at least 5 times a week for at least an hour a day will increase test scores. And in the past, the mean test score for chemistry was 67 out of 100 points. So when we look at that, the null, we should always think about the null is that it means no change. This is H0, we call it, and that means no change, the null hypothesis. So this would mean studying, and I'm just going to write it in shorthand, studying no test score increase. Or I should put that differently. No change, right? No change. And then the alternative. So the null means no change. The alternative hypothesis means that there is a change. So the person here believes that studying this often will increase test scores. So that means that there is a change. So this is typically what the researcher thinks is the alternative. And then the null is just there's no change or no effect taking place. So here, this would just be studying increases. And on the next slide, I have it written up better, okay? So let's take a look at that. So that was step number 1, where we wrote out the alternative and null hypothesis. And here I have them written in looking better. So we have mu, which is the population mean, equals 67 because that was the mean score. And then the alternative, so it doesn't change, it stays as such. And the alternative would mean that studying at least 5 hours a week has a positive effect on test scores. A positive effect meaning it increases. So the scores actually go above 67%. So here, the second step, what we're going to be doing here is just determining the level of significance. This is called the alpha level. And the alpha level we choose, or the researcher or we would choose before we collect the data, and we choose it at the beginning of the study. The reason being is we don't want to get all of our calculations and all of our data and then say, oh, I want the alpha level to be bigger. So we don't want to change it at all to fit what we want to happen. So this alpha level, quite often, and we see alpha levels of 0.10, 0.05. Basically for our course, we're looking at 0.05 most of the time, and 0.01 would be another alpha level. Now this would be a one-tailed test because the rejection region, let's say that our alpha level is 0.05. So the rejection region would just be over here where this area under the curve would be equal to 0.05 or 5% of the data. So, and here this mean would be 67. And what this means is if we did our calculations and found that our data from our sample was down in here, then we would reject the null hypothesis because it would be significantly greater or different than the 67, the score of 67. So this would tell us exactly where our rejection region would be, and we look at that before the testing is done. Now, when we look at this, let me move this down a little bit. Step number 3. So first we did the setting up the null and alternative hypothesis, and then we got the alpha value, or the critical, also known as the critical value, or the area where we have the rejection region, and we set that up, and then we make sure the data meet the necessary assumptions to compute the test statistics. So, for instance, the data is normally distributed. So this is a normal distribution. You can see it's like this bell-shaped curve where we have in the middle is the mean, and 50% of the data is to the left and 50% of the data is to the right of the mean. And you can see most of the data is close to the mean out in these tails. There isn't much of the data, and this is just a normal distribution. Now, basically, for the purpose of this course and the hypothesis testing, we're going to be looking at normally distributed data. Okay, so now the next thing, you ensure that you have normal distribution, and then step number 4, you would compute the parameters that are being compared by the test statistic. So that would mean, you get your sample and you calculate your sample mean and standard deviation. Typically, this can be tedious with a large sample, and you would do this using a spreadsheet software like Excel or SPSS software, or a calculator that had the ability to calculate things. And just to illustrate, the mean is always here, and if we what we do is we call it standardizing the normal curve. When the mean, we just call it 0. And then to the right would be 1 standard deviation away, 2, 3. And I go over this in chapter 3 video. So these are negative standard deviations away. And certain percents fall within 1 and -1 standard deviations away from the mean, and we look at this quite a bit in chapter 3. Just review there, and please watch it if you haven't. And now for number 5, step number 5, we would compute the test statistic and obtain the p-value, and that's the probability value of the computed statistic. So the chance of the statistic, the probability of the statistic occurring by chance, I should say. So we'll look at that. So here we have the sample size is 36. So sample size is n. And then we have the standard population standard deviation. And the symbol for that is called sigma, kind of like a scripted R. And that is 12.2. And then the sample mean, that is written as x bar. And the actual population mean would be the 67. So now what we're going to do, we know that the rejection region is here, and we're calling it 0.05, our alpha level. We'll say it's 0.05. And here we know that if we standardize, the mean would be 0. If we had it unstandardized, we can look at that too. The population mean, the actual population mean would be, or mu, would be 67. Okay? And let's see, and this is the rejection region, so let me go ahead and put that there. And 0.05. Okay, so now what we're going to do is we're going to calculate the z-score, okay? And the z-score will tell us how many standard deviations this data is from the actual mean. And the mean is 0 here, and then whatever we get here will tell us how far away from the mean this sample is. So we take x bar, which was set as 70. Get it up here so I have plenty of room. And minus mu, we said mu is 67, minus 67. And then this is being divided by sigma, which is 12.2, and then divided by the square root of n, which is 36. Okay, so we don't panic. In math, we never want to panic. We just take things step by step, break them down, make them easy. 70 minus 67, well, we can do that. 3, and then 12.2, here, divided by the square root of 36. I do this on my calculator, and that is 6. Okay? So now what I'm going to do is 12.2 is being divided by 6. So I'm going to divide it by 6, and I'm coming up with, I'm going to leave 3 up top, 2.033, and it's repeating. So then I take my 3, and I divide it by the number, and I'm leaving it in my calculator so that I get the exact number. So I get my z-score as 1.48. Okay. So this looks good. Z equals 1.48. we will take a look at that on the next page, but we computed our test statistic where we got our z-score, and there are different test statistics that you can use, but for the purpose of the course, I would know this one in particular. So I don't know that we'll be using any others. So okay, so let's take a look at this again. So we've got our z-score. We have z equals 1.48, and I rounded that. So I rounded it to the nearest hundredths place. So it was originally 1.4754, and since there's a 5 next to the 7, I round up to 1.48. And then I know this is the mean is always in the middle, and then 1.48. So let's say 1 is here, and then 1.48. It would be like between 1 and 2. So 1.48 is how far away from the mean this z-score is, or how many standard deviations from the mean. And then I also know that my rejection region, or level of significance, is 0.05, and that is in the right tail, because we're only concerned with having a positive effect, or the scores above 67. So here, and okay, so now I am not sure, 1.48, I am not sure how much area under the curve there is between 0 and 1.48. So I can easily look that up in my z-table. So let me go ahead and pull that one up. So I go here to look up my z-score. And the z-score gives me the number between, let me move it over if it will let me. Got that. So this Appendix B in the back of your book, and it is on page 515. If we go to this, and we go over here to 1.4, this is the z-score, and this tells us the percent of total area of the normal curve between the z-score and the mean. So when we think about that, diagram. So here's the mean at 0, and our z-score is at 1.48. This is going to give us the percent of area between the mean and the particular z-score 1.48. So that's what we're looking at. So 1.4, and then we have to scroll over a little bit. Let's see. So we'd start out here, 1.4, and we go all the way to 8. So 1.48 at the top. So it would be, this area here would be 43.06. So let's take a look at that. So this area here would be 43.06%. And this area is 0.05. Now, we also can look at, okay, what is this z-score going to be? That would be helpful, because then we can determine whether or not for sure this falls within the rejection region. So here, if this went out to 0.05, that would mean that 45%, and if we look at this as 5% of the data, because I'm writing in percents, so this actually would be 45% of the data. Let me see. So out to 1.48 standard deviations is 43.06% of the data. And then if we went out to here, our rejection region, so let's look that up, because from the area here to here, I should probably do this in a different color. So I'll override this. So maybe I'll just leave it. So if we looked at the area between 0 and all the way to here, this area under this curve, that would be 45% of the data. And if we look that up in our appendix, so we'd be looking it up the other way, because we've got the area, it's 45, and it's kind of in between here, between 44.95 and 45.05. So I'd probably just look over here, 1.6 and then 1.65. So this z-score, where for the critical value 1.65, it would start here. And here, this is close enough to the mean, and it's not in the rejection region, meaning it's close enough to the mean that we cannot reject the null hypothesis. So our conclusion would be that we cannot reject the null hypothesis. And sometimes the book calls it accepting the null hypothesis. So we cannot reject it. So the difference, there isn't a big enough difference. This is still close enough to the mean. It's not significantly different. It's not out in the tail. So hopefully that makes sense. So that was step number 6 of the hypothesis testing. So let's go on to the next idea. So here, know how to write and understand the null and alternative hypothesis. In the study guide, they have these letters large, but they're subscripts. So you want to make sure you are familiar that they look like this. This is what the null looks like, and then this is what the alternative. And okay, so let's look at getting the null and alternative hypothesis. So we have this scenario with a pharmaceutical company. Pharmaceutical company believes the vitamins they administer to pregnant women will increase the birth weight of their newborn babies. Okay. The birth weight of the population is 8.3 pounds. So I can write this as null. The null hypothesis means no change. Okay. So this would just mean that the birth weight of the population is 8.3 pounds. And it's going to equal that. There's no change, okay? With these vitamins administered, there's no change. And then the alternative would mean that there is a change. So this is saying increase the birth weight. So the company or the researcher, their claim is typically the alternative hypothesis. So this would mean that it increased the population mean birth weight of babies. So it would look like this, because it's an increase, it's greater than 8.3 pounds. And typically testing is done, this would be a one-sided test, and it would be down here. You would have some kind of significance level, and of course here would be the mean. And when it's not standardized, you just put in the regular numbers. When you standardize it, it would be 0. But typically, it's better to have a two-tailed test. Why? because what if these vitamins are actually having the opposite effects, and babies' birth weights are decreasing? So typically they recommend you do two-tailed tests, except for very extreme cases and scenarios, but always a good idea to keep that in mind. So, and typically they mandate to do two-tailed tests for things. Anyway, that was an example of one-tailed test, and we do look at one-tailed tests in this course, so good to know those. And then here we have a similar scenario with the chemistry, and then this is that we have our, much know this one, and we can write it out in words, or we can just write it out as the population mean would not change. The mean score would be 50%. And then the alternative, this just says it will have an effect. That means it will be significantly different than the 50%. So then we would look at both tails. Hopefully studying, and from my own experience, when you study more, you get better results. So study the stuff that the test is aligned with. And then you would have rejection regions in both of the tails. So, okay, and then this would be set up so that you could do a one sample z-test. Okay. Here, what is the critical value, and understand the difference between one and two-tailed tests. So we went over that a bit, and the critical value would this one 0, and then out here the critical, or let me put it as unstandardized normal distribution, where we have it as 8.3 pounds. And the critical value on this one, well, they're looking to see whether it increased the birth weight by taking these vitamin pills. So typically the alpha value that we see, especially in this course, is 0.05. That's a pretty solid one. And that means that when you go into this area, and we looked it up earlier what it would be in our Z tables. So that would be 45.05, 1.65. Why? Because that's the area that is not included in the tail, and this gives us the area of the normal curve between a z-score and a mean. So this is really 5%. The in the z-score table, the areas are written as percents. So 45% plus 5% would give us the total on this side, which is 50% of the data in the normal distribution, and 50% is over on this side, under the curve. That makes sense. And then here, just now here we would have actually two critical values on this, because we're just seeing if it has an effect on test scores. Studying has an effect. So what we'd be looking at would be, trouble grabbing my pen. Okay. So what we'd be looking at would be a two-tailed test, because the null hypothesis says mu equals 50%, and then the alternative states mu does not equal 50%. So if it's down here in the left tail or the right tail, either one would be significantly different than the actual null, and then you would be able to reject. And excuse me. So an alpha value of 0.05 for this statistical study would be a little bit different because we would split it up in half. So the area under each of the tails would be half of this. So we just take 0.05 divided by 2. You can do this on your calculator. 0.05 divided by 2 equals 0.025. And that would be in each of the tails, the area in each of the tails. And if I want to find out what this z-score is, well, then I'd have to say, okay, this is 2.5% of the data's here. I just converted this to a percent. And then here, so that would mean that this would be 47.5% of the data is here. And we always read the z-table for the z-scores. We find them by finding, it tells us between the mean, the area under the curve between the mean and the score. So we'd look this up. 47.5%. Oh, right here. So that would be, we'd look at the z-score 1.9 and then 6. See the 0.06, we just add the 1.9 plus 0.06 and it's 1.96. So that would be our critical value. 1.96, the one that's to the right of the mean, and then to the left of the mean would be negative 1.96. And this is how many standard deviations away from the mean the critical value is. So it's 1.96 either, and then negative because it's to the left of 0. To the left of 0 is a negative number. Okay. All right, so what is the alpha level or level of significance? So we've talked about this a bit. The alpha value is the level of significance, and these are commonly used alpha levels, 0.10, 0.05, and 0.01. They can also be written as percents, typically, unless they're in the unless they're showing under the curve, they're written as decimals. So, and they're far enough away from the mean that they're in the tails and they're significantly different than the mean. Now, another term you want to be familiar with is p-value. And this is the probability value of a statistical test. And it represents that the results were obtained by chance alone. And the p-value is calculated from the data sample, and it is found at the end of the statistical test. So let's just take a look at that. So let's say we have a one-sided test. And here's our mean, normal distribution and everything. And then let's say we have 0.05 as our rejection region. So area under the curve we'll call 0.05. And let's say that we get a p-value of 0.065. So 0.05, that's like 5% of the data occurring by chance alone would be there. So it's not very likely it's going to happen. It's kind of, and if you were a gambler, you would not want to gamble on this at all. You'd want to go the other way And because 95% of the time, by chance alone, things are going to happen somewhere else. And they're going to fall someplace else. So, it's very significant. It's very different. It's significantly different. And a p-value, if we had this as our significance or critical value cutoff area, and we calculated and we got a p probability of um, this occurring as 0.065. So that number is actually bigger than our 0.05. So 0.065, oops, 0.065, that would be outside of the rejection region. It's closer to the mean. So it wouldn't, if we had this as our statistical level of significance, we would not reject the null hypothesis. Now, if we had 0.10, well, then this would actually be in the rejection region. And my diagram's not drawn to scale, by the way, but if 0.10, let's say 0.10 looked like this, and it's not drawn to scale at all, but 0.10, well, 0.065 would be lower than 0.10, so we'd be inside the rejection region, and we'd be able to reject the null hypothesis because it would be significantly different. Okay. All right, probability of a type 1 error, also known as the alpha value. This occurs when the null hypothesis is rejected when it is actually true. So what's happening, and here are the alpha levels that we've talked about, the 0.10, 0.05, 0.01, and this means that these chances of these are the probabilities of making a type 1 error. So the smaller your rejection region, the less likely you are to make a type 1 error. So if you're all the way out at 1% or 0.01, you're way out in the tail. So it's not likely that you're going to get a type 1 error, only 1% of the time, statistically speaking. So anyway, 0.05 also, going to happen 5% of the time, so not very often that it possibly occur. So here, let's take a look at what a type 1 error, what that would look like when we have the null and the alternative. So it's when you reject, the null is rejected when it's true. So that would mean in this case, we would reject that mu equals 50 when actually it is true. Okay, so we just look at the null, and what we do is we for a type 1 error, we reject it when actually it is true. So important to know how to word this and, practice that, get to know, it's fine to do this example and practice it for type 1 error. And then also, we're going to look at a type 2 error. It's a little bit different. This occurs when the null is not rejected when actually it's false. So we're not rejecting the null even though we should. And this is also the probability of a type 2 error. It looks like a B. It's called beta. And the alpha and beta values are related. So they have a relationship where if you increase one, the other decreases. So it's an inverse relationship. And we don't get into calculating B values. So just know how to interpret a type 2 error. So here, a type 2 error, we're saying that the null is not rejected. So not rejecting, or sometimes your book calls it accepting the null. That 50, that equals 50, or the population mean equals 50, and that studying at least 5 hours a week has no effect on test scores. When, it significantly different than 50. And you can practice, they're in your book, they have different null and alternative hypothesis statements, and you can look at those and try and do those for type 1 and type 2 errors and kind of get a feel for those. Now, here we have the level of confidence. And this is 1 minus the alpha, which is the significance level. And we talked about that. And this is the probability value associated with a confidence interval. And if we talk about alpha quite often being this 0.05. So if alpha equals 0.05, and this is picked before the testing begins, then our confidence level will be 1 minus 0.05, which is 0.95. So it's like $1 minus 5 cents here. And that's 95 cents or 95%. Just to change to percent, you just move the decimal 2 places to the right. And that should be it. Okay, so this, we just looked at on the last screen. And here is a formula for the standard error of the mean. And this is just right here. And all you need here is the sample standard deviation and the number in the sample. So we have this information. So let's take a look at the scenario, because I like doing examples because I like illustrating, so it makes sense and something's concrete with this. So, and we're going to look at getting the confidence interval. So here, what we're going to do is we take the sample standard deviation, which is 2.16. And I want you to know this formula to know for the assessment. I don't know if you'll be calculating it or not, but important to know it. And then what I do here is I take the square root of 70. So I do on my calculator square root and then 70, and I get like this number 8.366 repeating. This is repeating, and then on top it's 2.16. So 2.16 divided by 8.66, and then I come up with a number which is around 26. Okay, so, and this, I didn't put the formula up here, but this is just mu plus or minus, and then this is for alpha being 0.05, 0.96. And we looked at that earlier. If alpha is 0.05, let's look at that again. and it would be 1 point, oh, so alpha isn't 1.5, so 1.9. Okay, so alpha is 0.05, but it's for a two-tailed test, so it would be 1.96 would be this value for a two-tailed test for an alpha level of 0.05. So here, times it by 0.26. And our population mean is 8.3 plus and minus 1.96 times 0.26. So let's make some sense of that. Order of operations tell me that I have to multiply before I can add or subtract. So I'm going to do 1.96 times 0.26, and I come up with 8.3. I didn't do anything to that, plus or minus 0.5096. So our confidence level is 95% confident that the true mean weight of the babies taking vitamins distributed by the researcher is between, and then we'll subtract 8.3 minus 0.0596, and I'm getting 8.24, and add that 8.3 plus 0.5096, and that is 8.81. So basically, this tells us that we're 95% confident that the true mean weight of the babies taking the vitamins distributed by the researcher is between 8.24 and 8.81. Now, power, you just need to know some basics on this. This can get complicated, a bit complicated, and like I said earlier, we're not going to be calculating the value for beta, which is the probability of a type 2 error. So just, kind of know like the facts on this. Power of a test measures the sensitivity to detect a real difference. This, the power of a test is equal to 1 minus beta, and beta is the probability of committing a type 2 error. If we somehow knew beta was 0.08, then the power would be 92%, or 1 minus 0.08, which is 0.92, that yields 92% to a percentage. There is a bit of balance on these different variables, alpha, beta, power, and the book wants you, states that you want your power to be 80% or above. So that's good to know. So I just kind of know this. You don't have to know all the details on power. It's kind of out there, and we don't go into it that much. So okay, and then so understanding the concepts of type 1 and type 2 errors and how we minimize the type 1 error and type 2 errors. So here we increasing sample size. The better your sample, the closer you are going to be to matching the population and making correct conclusive statements about the population. So definitely increasing sample size is typically always a good thing to do. There is an inverse relationship between type 1 and type 2 errors. As one increases, as alpha increases, the beta decreases. So, there's a balance between it. You don't want to increase one so much and decrease the other so that you're going to get that type 1 error. So just something good to know. You don't want your alpha to be um, you know, large, and then you're increasing your error. So anyway, really helpful to you're increasing your type 1 error when you decrease the probability of type 2 error, and just a delicate balance, and it goes beyond this course. So, wow, that was a lot. So, questions, please contact course mentors. And this is our email, nursingstats@wgu.edu. We'd love to hear feedback and anything we can do to help. We're here for you. So good luck and great job watching the video. Hope this was helpful and love feedback on it. Thanks. Bye.